Hey everyone, welcome back. Week 5, the final week right here, prototyping and mechanical engineering. I am Will Fisher, and I am your guide through the world of mechanical engineering here. Today we're going to be talking about motion and gears and moving stuff and all that sort of thing, which should be really fun. I just want to remind everyone before we hop in that there are some quizzes, and so if you wish to take them, I believe Hackaday will give you like a certification that you've completed the course if you can pass those quizzes. I realize, given how quickly we move through all this material, it may be helpful to go and watch YouTube of these classes afterwards, so you can kind of get everything. But those, you can get that certification going. So without further ado, we're going to jump right on in. Just to introduce myself again, my name is Will Fisher. I am a mechanical engineer. I've been doing engineering for more than a decade now on a variety of different fields. I'm a freelancer, so if you have a project, you can hire me. And I also teach, so I can do that as well. Let's jump in. It's movie break time because we're only a bit in. This one I like a lot. Hopefully I've got my audio shared, so I want to make sure that I've got my audio shared on this. Yeah, sorry, I was not sharing computer sound because this one is a beautiful thing.
The missile knows where it is at all times. It knows this because it knows where it isn't. By subtracting where it is from where it isn't, or where it isn't from where it is, whichever is greater, it obtains a difference or deviation. Okay,
so I have this in there because I think it's really funny, and I just figure it's a good way to think about motion. You know, and a lot of times you're thinking about where you are, but sometimes you need to think about where you're not and how to get there. And it's an interesting frame of reference to use. I mean, this is clearly kind of comical-ish. But it's good to have that kind of reference. So we'll move right on in to a motion. And then after that, we'll look at power transmission. And what I mean by that is how you get power from one thing to another, like a motor into a propeller, something like that. Then we'll talk about linear actuation. So that's the kind of where your power comes from, and rotary actuation as well. So that's stuff moving in a line as compared to stuff rotating around. Cool, let's go into the intro stuff. Today is going to be pretty heavy on math, but it's all algebra. And so it won't be difficult math, just a lot of it. So we'll jump in on that. First of all, I want to define motion. Motion is just stuff with mass, and that's important, moving from one place to another. And mass follows Newton's laws, specifically inertia. And that is, a body at rest will stay at rest unless acted upon otherwise, and a body in motion will stay in motion unless acted upon otherwise. And that's a pretty important thing, that that inertia is kind of the mechanical and physical space equivalent of induction in the electrical world. And it's just this idea that once you're doing something, it's going to stay doing that thing, whether it's still or motion. The second one is Newton's second law is one we're going to spend a lot of time with today, and that is force is equal to the mass times the acceleration. And so that you can play either direction. You can either start with an acceleration and a mass and figure out how much force went in, or you can start with a force and play it the other direction. We'll spend a lot more time there. And the final one is every action has an equal but opposing reaction. So for example, you exert a force on the floor, assuming you're on a floor, and it exerts an equal force back up in the other direction. And in the case that those forces were not equal, there would be motion, that F equals ma. So that's an important way to think about things, though the math we're working on today won't go too far into that. Today's class will be a warming blend of practical and theoretical. A lot of theoretical is going to be the mathematical side of things. And as we jump in, I do want to take a quick note here of this image over here on the right side. That's what we mechanical engineers call a free body diagram. And that's where you take something by the center of mass. So here you have a block on an inclined plane with a pulley. And so these are the two masses that you see, and you can look at all of the different forces that are at play here and how they balance out. And that's a really important way to think about whether or not stuff is going to move around on you. And so you'll see those a couple of times further on in the presentation, but just to give you an idea of what it is you're looking at, that's what those are. Okay, Newton's second law. Like I said, we're going to get right into the depth of this. So it's that force equals mass times acceleration. Acceleration is the movement of something increasing in speed. So you have distance, and then distance per time is rate or velocity if it has a direction to it, and velocity per time is acceleration. So it's the second time derivative of position. Mass is a material that is a property that all material has, which is it weighs something. And in this case, its weight is the force of gravity on it. I'll talk about that in a little bit more in a second, just to kind of clarify. I realize a lot of these things kind of get confused. Anyway, so what we look at, the unit of force in the SI world is the Newton. It's abbreviated N, and that's a kilogram times a meter per second squared. And that's just a very standard unit. And we're going to look at units as a way of explaining phenomena, and that kind of helps us all get through it. Torque is with the same exact principle, but taken into a rotational frame. So we as mechanical engineers, oftentimes find things spinning around. And so it's helpful to just multiply that stuff by the radius it is away. So, and that happens for angular velocity as well. And it turns out that that radius component drops away, but if it doesn't drop away, you have different forces acting at different radiuses away from a thing, then that's a really important thing to calculate in the way that you rotate something. So a torque very close to the shaft can be counteracted by a relatively minor force far away from the shaft of large torque. I'm not going to talk too much about torque and the rotational frame simply because we just don't have time for that. So I'm going to do everything pretty much in a linear and translational frame, and you can extrapolate that to your rotational frame on your own. Work is an important component of this as well, and that's the product of force, which is mass times acceleration, times the distance over which it operates. And so normally this would be, you would get into the calculus of this and it would be integrated over the distance. But in the case of something that is constant, the integration comes out to just be multiplication, which is really convenient for us. So we're not going to do anything more complicated than that. We'll just give you an idea of what's deeper under the hood here. And that unit is a joule. A joule is a Newton times a meter. And so oddly enough, that Newton times a meter is the same as you would get from a torque over here, which is also a Newton meter. But in the case of work, you're thinking about it, the force operating over that entire thing. So while they look like the same unit, they are in fact not the same unit. So here you've added that meter into the top. So if you look closely there, you'll see that I've squared my M. So it's a kilogram times a meter squared per second squared. Cool, moving right along. Energy is in the same units as work in joules, and it can be used to do work, though it isn't necessarily the same thing because it can be a lot of different things. Energy can also measure losses to heat, and it is always conserved. And what that is that in a system that you have, the amount of energy that goes into it will always come out in some form, eventually. And so that's a really important thing. But if you think about this, if I'm doing work, I'm putting some work in, maybe it's electrical energy and it's coming out as rotational energy, there will always be some loss there towards heat. Nothing has what we call perfect efficiency. So efficiency is down there at the bottom. Efficiency is commonly used with that kind of loopy N shape, which is cool. And that is a ratio of the useful energy out from your system. So whether that's you're compressing a spring or you've rotated the thing a certain number of revolutions or something, divided by that energy in. So it's always going to be a number between 0 and 1. It'll never be above 1. If it is, come find me. We got patents to file. But if it's not, it should be in that range. Now it can get very, very, very close to 1. And sometimes you find things when something is, quote, ideal, then you just assume it has an energy, an efficiency of 1. But in reality, nothing has perfect efficiency because reality is not what theory tells it should be. Okay, so let's think about what we've got to calculate here. So there's a lot of different types of energy. Did I skip a slide somehow? No, I guess not. There are several different types of energy here. The first is that we're going to talk about is kinetic energy. And so that is like how much energy you have in a moving object. So if you have a car moving at a specific speed, the kinetic energy in the car is modeled as 1/2 times the mass of the car times the square of the velocity of the car. If you have that car go off an ideal ramp, a perfectly efficient ramp, go straight up, you can guess the height of it based on the mass times the acceleration of gravity times the height. That's potential energy, gravitational potential energy. It's going to then fall right back down, and assuming it hits its ramp and there's no friction, it will end up going the other direction at the same speed, which is kind of a comical thing. We call this the Roadrunner effect. But that is actually, and you can calculate the height it goes up to, and you know that as it comes back down, assuming that everything comes back down the right way, and there's no friction in the system, so no energy lost to heat, then it will end up moving back out of the ramp at the same velocity that it came into the ramp. Wild. Okay, that's the conservation of energy at work. You can also store potential energy in a whole bunch of other different ways. For example, mechanical energy can be stored in springs. So you compress, and then when it releases, it can create this fast moving object. So that would be something like if you have a spring-loaded catapult, or like a trebuchet uses the gravitational potential energy, counterbalances it, and then it converts all that pretty efficiently into velocity of a much smaller mass, which is cool. That's how it can launch so far. You can do the same thing with like a bow and arrow. You have this kind of spring potential as you draw it, and then as you release it, out it goes into that kinetic energy. So this can be a really convenient way to calculate stuff. There's other potential energy stored in other places. The potential energy inside of a bullet is stored chemically, for instance, and then it explodes, and that creates a large amount of energy, which then you convert through to be kinetic energy in the case of a firearm. And there's other ways out there as well I won't get into. So let's take a look at an example here. So let's say we've got a spring. We're going to crank it all the way down. We're going to put a mass on top of it, and then we're going to release it, and we're going to see how high our mass goes. Okay, so throughout this entire thing, we're going to assume that everything is operating with perfect efficiency so that we conserve energy throughout the entire example. So we're going to start with our potential energy from a spring. That K is a spring constant, and that is a listed property. When you purchase a spring, it'll tell you the spring constant. So we're just going to choose, I chose here arbitrarily a spring constant of 12. And then we're going to see what happens as this goes through the system. So we have this thing, and we're going to see what happens if we put a 1 kilo object on top of this spring that we've now compressed 1/2 meter. And then we're going to see how high it goes when it comes out the top. So you can see there that I've taken this value here, 12 times 0.5 squared. So that's what, 1.5 joules is my unit here. And then I'm going to see what 1.5 joules of energy will do in terms of the launch velocity. That is the velocity that's moving right as it leaves the spring. And then I'm going to convert that velocity into height. I could convert straight from the spring energy to height, but I'm curious to know how fast my object is leaving the thing. So it turns out to be the square root of 3. So if we multiply that 2 on through, that's and then we take the square root. So our velocity is the square root of 3, which is about 1.73 meters per second, which is pretty quick when you think about that. That's fast. So we want to see how high this 1 kilo mass is going to go. So the gravitation, like the acceleration of gravity at sea level on Earth is 9.81 meters per second squared. That's just how it is. You can look that up in a table. But then we can figure out our height. So we now have an object that's moving, that we know has 1.5 joules. It's moving at 1.73 meters per second. So we divide that 1.5 joules by our acceleration to get our height, which is 0.15 meters. So this thing's pretty heavy, so it's not actually going to go all that high. It's going to launch really fast, and then it's going to kind of ground right back into the Earth there. Cool. So moving along, power is kind of the next thing here that we want to look at. And so power is what happens when you look at work over a period of time. And so when I say over a period of time, I'm dividing by my time. So it's an average amount of power, of work per time. And you would do this with calculus normally, just like the other things, but we're not getting into that today. So the unit of power is the watt, named after James Watt, who refined the steam engine into a usable form and spurred the Industrial Revolution. Interesting dude, look him up. And it's a joule per second. So what that means is we now have kilograms times meters squared over seconds to the third. And that is kind of a useful measure for us in terms of measuring the amount of power in a system over a long period of time. We'll come back to that, I think. I should have reviewed my slides a little more closely this afternoon. So gravity is an acceleration. It's not it creates a force based on the mass. And the gravity at sea level is this 9.81 meters per second squared. So the force of gravity is that 9.81 times our mass. That's why a heavy object applies more force. If I put a feather on my finger, it doesn't weigh much. So the weight, the force that it creates is not very high. But if I increase that mass to a 20 kilo boat anchor, then it's going to create quite a lot of force on my hand also. So we can look at the work done to raise that a 10 kilo object 1 meter. So we multiply that out. The work of gravity is 9.81, that acceleration we had, times the 10 kilo weight, times 1, which is our 1 meter, and that's 98.1 joules. So that gives you an idea of how much power there. And let's say we wanted to raise that in 30 seconds. We're now going to take that 98.1 joules and divide it by our 30 seconds, and that would require 3.27 watts. And you think that's not very much, and it doesn't sound like much, but a 10 kilo object is pretty heavy. But 30 seconds is a long time. Like, I've spent less than 30 seconds so far on this slide. It is creeping up there, right? So you can use a relatively small motor to move a lot of weight, potentially. And that's why I'm talking about this stuff now, is when we think about how we size our motors later on, we'll want to think about that in terms of watts. And so you want to figure out the job you have to do and then spec your motor accordingly. So that's why we're talking about all this math now. Okay, so let's check and do a sanity check on this and see if our units make sense. So we have all of these things, and we're going to take a look at the units. So we have, we can take our 9.81 meters per second squared, our kilogram, our meter, our second. We can take all of our numbers out, and we can say, okay, so there's a meters squared, kilograms, and seconds cubed here. Oh, look, there's our watts out there at the end, kilogram, meters squared per second cubed. Et voila, we have our watts right there. Beautiful. That's a nice way to check and make sure all your units are working out, to make sure you haven't accidentally multiplied by 10, used centimeters instead of meters, so on and so forth. This is a really convenient way to make sure you're doing it right. Power comes with trade-offs, as always. As we know from our formula, we have this kind of this divisor in the middle. So we can start with a medium amount of power and do a medium amount of work in a medium amount of time. If we want to do a lot more work, we can increase the amount of time the same amount. So we can spend 5 watts to do, 5 joules in 1 second, or we can do 50 joules in 10 seconds. We've just, the same amount of power going in is used over a longer duration to do more work. Same thing goes exactly in the other direction. That's that third line there. We want to do a little tiny bit of work in a little tiny time, we can do the same thing. But if we want to decrease the time at which it takes us to do our work, without reducing the amount of work we do, we have to increase our power. And the same thing goes the other direction, right? This kind of makes sense intuitively, but the nice thing is there's a mathematical relationship here that allows us to model it. And it's relatively easy to use. Moving along to something else. Okay, so I realize I am moving through this material really quickly, and that's because I want to get to some of the really exciting stuff in the power transmission parts. Stability and control. This is a trade-off also. We'll talk about that in a slide or two. And I want to say, you use control systems to move things where you want them to be. Stability is the tendency to stay where you are. It works a lot like inertia, right? If you want something to fly straight, you want it to be pretty stable. So like in big cargo aircraft, they put the fuselage below the wings, and then the weight, the force of weight, keeps that plane very steady as it's flying. You don't want that for a fighter because you want to be able to move very quickly. Those cargo planes don't roll over very quickly, and they certainly don't bank very quickly. So with a fighter, you put everything pretty close to the center of mass so that you can rotate and pitch really quickly. The result of that is that you have very good control, but very low stability. And in fact, these are F-18s shown here. When they initially rolled these out, the pilots would get unnerved because there's an electronic control system that would control the ailerons, the flaps on the back of the planes. And they would look outside at certain speeds and they would be fluttering in the wind. And it wasn't actually that they were fluttering, it's that the computer control system was moving them to maintain that stability artificially, even on a straight flight, so that they could have that really high level of control later on when they need to be doing extremely nimble aerobatics, as they're called. And just kind of as you think about this, you can think about this as a pendulum, right? If I want to be able to move that pendulum with a motor, I can shorten my length or lower my mass, and I can move it more quickly. But the thing is, it's then much stable. If the wind comes along, it'll blow that much more easily than it would if I have a big weight on the end there. Cool. So here's the same thing you can think about in control and stability that we talked about earlier, kind of with power. If you want to increase your stability, you're going to, by default, for the same amount of power, decrease your control. So these are inversely correlated. And so same thing goes the other direction, or you can crank up your power, get a lot of stability and the same amount of control, or a lot of control and the same amount of stability, right? It's all kind of intuitively makes sense, I hope, now. Cool, let's take a look at some control systems here. We'll move along here. This is a control system that has one of the classic things called an inverted pendulum. So we're gonna watch it here. As it moves, it's going to try and swing the pendulum up to the upright position just by moving back and forth. This is really hard to do as a human. Look at that. Ah, so nice. But that pivot that you see is actually a free pivot. And that's one of the classic problems of control systems, is how efficiently can you do this thing? Turns out that's a really difficult mathematical question. We're not gonna get to it, but it requires some knowledge about control systems. And I'm just going to touch briefly on this. And this is one of those slides that's like an entire PhD. Entire PhDs are done. This is an entire field. Control theory is an entire field that people spend their lives researching. And I'm doing it in a slide. So I'm sorry to those people who do that stuff, because you are working real hard. So this is hopefully an answer to the fundamental question of how do I get something to where I want it to be? And this is a fundamental part of robotics also, because as you try to have an arm grab a thing, you need to know where the arm is, and you want to get to that location. And so you can do this one of two ways. If you don't have information about your system, you could kind of dead reckon, and that's called open loop control. And so that's if I like close my eyes and I just reach out for a thing and try to grab it and I don't know where it is at all, that's open loop control. That can work sometimes. You can count how long a motor is on and get it pretty consistent, particularly with something like a stepper motor, which tends to be pretty consistent in the distance it goes. But if you do that 100, 200, 5,000 times, you're not going to get necessarily repeatable results. And that is not ideal, right? And the way to solve that is by plopping in some state information to your system. And you do that with sensors. You can do that with a simple sensor, like a switch that you bump into. Every third time on your motor, you swing back and you swing until you hit a switch, and then you know where you are and you can go and you can calibrate it. And that's still not exactly closed loop control. Ideally, you have something like a rotational encoder on there that tells you exactly where you are at all times. So as you try to move to a specific location, you know when you're getting close and you can slow down before you get there. Because remember, inertia is kind of the enemy of your control system. It's going to try to keep moving even after you stop moving. So if you move to the location and then stop your motor, it's too late. Your inertia is going to swing you a little bit past. So you need to start slowing down your motor effort before you get there. And there's a large amount of control systems out there that will do this. Some of them that are very, very, very complicated and very efficient. Some of them that are pretty darn efficient and not that complicated, like the PID controller, which is kind of like the bread and butter of your control systems. It was invented back in, I don't know, maybe the 30s or 40s. I'm not exactly sure. But it's still used today because it's so simple to implement. And so that's the one I would recommend to most people who are trying to do a control system. You can get more elegant than that. You can dive much deeper into control theory if you choose to. Yeah, so that's kind of control systems in a very, very, very short nutshell. And basically this idea of open loop versus closed loop is pretty important. And as you try to have higher and higher precision, you're going to need that closed loop, or else there's just no way you can hit it with an open loop system. Cool. I want to talk about degrees of freedom also. Degrees of freedom are a really interesting thing. Mechanical systems are defined as by their degrees of freedom. And what I mean by a degree of freedom is the way in which it can move. So if you have a motor, we'll talk about these later, a motor has a single rotational degree of freedom. Assuming the motor body is fixed, there's only one thing, and it's a degree of freedom that's rotational. A slider, on the other hand, has one degree of freedom, and it's translational. A free body, that means something just floating there, has 6 total degrees of freedom. It can translate in any of your Cartesian directions, and it can rotate along any of those axes, right? And so when you are designing something that you want to move, you want to think about what your degrees of freedom are. Some of them you would like to constrain so that you get just simple rotation, means you've constrained 5 of 6 and left 1 free. Or sometimes you want something that's going to have multiple degrees of freedom operating simultaneously. And so if you're building something like a robotic arm, those can be 5, 6, 7 degrees of freedom at the end effector. So you have a thing kind of moving around. But even a human arm usually is modeled as kind of 7 degrees of freedom. So you have 3 rotational here, 1 rotational at your elbow, and 3 rotational at your wrist. And that's a reasonable mathematical approximation, though it turns out that it's a lot more complicated than that. And we're really good at using them. But if you have multiple motors linked up in a row, you might have a multi-degree of freedom system, even though each one is only operating on a single degree of freedom. And that allows you to get to where you want to be, because you're going to control all of those things in your software and your electronics independently. And so to try and get smooth motion out of them eventually, you need to think about that, like, okay, if I need to be able to rotate this thing and translate this thing, okay, those are 2 different degrees of freedom. I'm going to need 2 different actuators, because you need an actuator per degree of freedom in order to get them to operate independently. If they don't operate independently, maybe you've synced them together with gears, then it's only a 1 degree of freedom system. And that's actually really convenient. That can be a really nice way to do it. And you see this sometimes out in the field where, gearing or linkages create a single degree of freedom system. So I'll show you a really cool single degree of freedom system when we get to the linkages stuff later on. But I do want to show you this, which is a really, really neat example of a 486 degree of freedom system. So far as I know it, it's one of the most complicated things. This is a piece of artwork that some of my friends made. It's called Morph. It's a kinetic art piece. Each one of those panels is independently operating. And those LED panels kind of do this. It is mesmerizing to watch for hours. Fortunately, this video is only 12 seconds long, and it's gonna loop. No, let's not do that. So that's a lot of degrees of freedom, and each of them is translational. So they're all kind of moving in and out, and they use these NCLAs, which I'll talk about to do that later. Okay, we're done intro. Nailed it. We're only half an hour in, so power transmission, let's just jump through this. All right. There are a whole bunch of different types of power transmission. I'm going to go over 3 of them, and then we're going to look at the math and then the types of gear trains and how that works. Because my hunch is that the most useful stuff to you guys is this is the kind of math of power transmission. And so onwards we go. So here's some linkages. I'm just going to spend 1 slide and 1 movie on linkages, but you see them out in nature all the time, not nature, in mechanical nature. In the case of this right here, this is an engine crankshaft for an adjustable compression ratio engine, which is super cool. So you see that there are connecting rods and things. These are linkages, so you have rotational degrees of freedom between them, but then they don't translate, so you can fix them in places. So this is a 1 degree of freedom system in that you have you've constrained it such that the rotation of this element, it becomes the translation of this element, assuming that you're not threading in and out adjusting this thing. Similarly, this is a 1 degree of freedom system. These are mechanically tied. So even though you have multiple things all moving together, that little thing crawling over there, it's actually a single degree of freedom system, which is super cool. They are excellent for things like odd trajectories, as you see with the moving legs down there on the right. They're also really nice for converting between linear movement and rotation, as you see from the crankshaft there. And they are great because they give you reliably synchronous movement. And what I mean by that is if you need things moving together, linkages are really nice for that. So they're a good tool to think about when you're designing stuff for those things. They tend to be difficult for some things like vibration. And because you're using a lot of physical elements, they can have higher inertia and they can be kind of heavy. So they're not great for some applications where you need it to be light or where you need it to not generate vibration, which can become acoustic noise, which is unfortunate. Okay, let's take a look at another movie here. This is a buddy of mine who works in this co-working space named Flo, and he creates these incredible linkages in kinetic artwork. That's him demonstrating it, but you can see this thing as it goes around. You've got a whole bunch of linkages, but this is still a 1 degree of freedom system. That degree of freedom starts out with a rotational actuator, and then it becomes all of these different really cool translational elements as it goes, which I just think is the neatest stuff. I would definitely recommend following him on Instagram. He's great. One of my favorite Instagram accounts. Okay, let's talk about belts and pulleys. We're going to do this in I think one slide. Flexible linkages covers a lot of different things. It can be belt, it can be rope, it can be like steel braided cable, and it can be chain kind of. So chain usually has one degree of freedom in which it's really flexible and a degree of freedom that it's not. So it's not particularly flexible in the other, but it's not strong enough that you could really rely on it to move in that direction. I guess you could also think of a tank tread as a flexible linkage. And the fundamental of this is that they operate great in tension, but as you compress them, they buckle basically immediately. If you think about trying to compress a rope, you pull it taut, it stays great in tension. The moment you go like this, it's already buckled under the force of gravity. It's sagging like that, and that's what defines these things. So you can use pulleys to redirect that tensile force. Pulleys do not redirect compressive forces. And if you think about this, it's kind of evident. If you think about that guy standing in the thing, if he starts pushing on this to try and get the block to move down, it's not ever going to move faster than, like, you know, he sets it down on the thing and keeps pushing to try and push it into the object. It's not going to work. The rope is just going to buckle immediately because it's flexible. So you can use these things to create mechanical advantages by doubling. And by doubling, what I mean here is that he's pulling on the load, but actually the load is being distributed between this one line here, the right line, and the left line on those. And that allows him to move twice as far, but distribute the load between those two. So that block and tackle, that's a simple block and tackle. That's how you get the mechanical advantage out of that. The pulley itself just redirects the forces, and it allows you to redirect them in such a way that you can double them or more. So that's a super cool thing. If you need your belts not to slip, which is a major thing if you're using, say, steppers to drive something, which you use commonly in like 3D printer applications, timing belt is nice because it locks into your pulley or your pulley wheel. And chains also, because they synchronize onto sprockets, they don't slip. If they do, you have done some terrible damage to your system, and I'm impressed really more than anything else. So what you can always know is the direction of rotation in this particular, so the example that I've got down here in the bottom, you know the rotation is going to be in the same direction, so they're always going to rotate in that same direction. And the effective gear ratio, which I'm going to talk about as we get to gears, is the drive over driven. And so you can kind of see that here. If I shrink my radius, I'm going to have higher gear ratio. And if I increase it, I'm going to have a lower gear ratio, which gets me more torque out. And similarly, my work in is equal to my work out times my efficiency. And so I can say, hey, like my smaller gear is going to move more quickly and my larger gear is going to move more slowly. And this works the same way that gears do, which is why I'm not going into it too deep right now. Whew, we made it to gears. 35 minutes past the hour, and here we are. Okay, so these are spur gears, and I'm going to talk about the different types of gears in a second, but this is the cleanest example of kind of how gears and gear design works. Where you have this line of action, as it showed right here, that angle with respect to the tangent is what's called your pressure angle. And so when you design, you choose your pressure angle. And that shows you, here's some examples of what different pressure angles look like. You can't really go much below 14.5, which is a really conventional pressure angle, because the teeth get too thin and they start to snap off. You can go to these really high pressure angles, but you start to lose efficiency at the higher pressure angles. You also, module is commonly used for gear size, and that is represented in millimeters or inches. And so you would choose like a module 1 gear is in millimeters, and then your manufacturer will know, and then they'll know the size of the gear based on the total number of teeth. You could also give them a pitch diameter, and they'll figure out how many teeth go in there. But the problem is if you specify that wrong, you can end up with a fractional number of teeth, which of course doesn't work as a gear. So it's easier to specify tooth count, module, pressure angle when you're specifying a gear in a mechanical schematic. And you would also always specify the material when you're getting this made by someone else. Cool. And I've got this image on here so that you guys can go back and look at it if you need to. You mount with the center distance, which is this pitch diameter, the pitch circle, halved the diameter, plus the pitch circle half of the pitch diameter from the other gear, and that tells you your mounting distance. When you have gears operating together, you end up with backlash. And what this is if you're rotating one direction, you get this perfect synchronous motion. As you rotate back the other direction, it takes a fraction to move. And that's something to pay attention to as you get more and more gears together. The backlash adds up between them. So if you have only 2 gears operating, you have some backlash, but if you run that same gear system back to back to back to back to back, you now have 5 times that much backlash. So you're going to start spinning in one direction, and when you go to reverse it, you're going to spin for, maybe a quarter of a rotation before you actually start moving the other direction. And if you're using something where your sensor is on your motor, then you may have very, very peculiar outcomes on the kind of the end effector of your thing. It's difficult to prevent, but it can definitely be minimized based on your gearing selections. And I'll talk about that in a second. But basically, it is a massive headache for your roboticists because you need precision in your movement. And this is just the killer of precision, which is a bummer. Okay, we're going to talk about gear ratio. And I'm going to take a swig of water so that I don't lose my voice. Sorry for the wasting time. Conveniently, the ratio of radius, diameter, and tooth number always mix the same way. So your radius of drive over driven, your diameter of drive over driven, and your tooth number of drive over driven will always be your gear ratio. And this is really nice for your design. And this is really convenient because oftentimes gears are specified by tooth count. And so when you're thinking about designing yourself a gear system, that is a really nice way to do it. You do it with those numbers. If I have multiple gears moving along, I take the output from one shaft and put it into the input of the next shaft, then I can multiply the gear ratios from drive to driven, drive to driven, drive to driven, so on and so forth. So let's take a look at a quick example. I start with a 2-start worm gear, and I'll talk about this in worm gears, but that's effectively a 2-tooth gear, pushing a 24-tooth spur gear. The shaft of that spur gear drives a 40-tooth spur, which then itself drives a 60-tooth spur. So now I can multiply that gear ratio together. So I take my 2 over 24, that's drive to driven, my 40 over 60, the drive to driven. I multiply those together, that's 0.083 times 0.66. I get 0.055 as my total gear ratio. And so what that gear ratio effectively means is that my output shaft moves 0.055 rotations for every rotation of my input shaft. So I'm really cranking around on my input shaft, and my output shaft is just barely moving. Why would I do this? Well, my output shaft is going to have a way greater torque than my input shaft, which is really awesome. So my torque ratio is, my gear ratio lives in the denominator of my torque ratio, and then my efficiency live up top. So I'm going to multiply out all my efficiencies. That's what that big capital pi is. So the product of all of my efficiencies, I'm going to then divide that by my gear ratio. So I'm going to be generating 12 times as much torque on that output gear as I had on my input gear because of this worm gear plus my spur gears, which are geared in the right direction. So I would note that my rotation is 18 times slower. So I'm losing a ton of power to this inefficiency, right? Like I'm getting a 12x torque multiplier, but my rotation is now, my speed is 18 times slower. So it's a bummer of a trade-off, but that is the loss of heat. What I get for that is worm gears are extremely high ratio to their, they're extremely efficient in terms of their packaging size. And I'll talk about those when I talk about worm gears specifically. Okay, practical example. It's going to take me a second to pull this up because I'm pulling up calculations from my previous company. So it's going to take me a second. I'm sorry. I should have had this a little bit better prepared. Sorry. So sorry. I'll go late for this, I promise. Loading. Nope. Okay. Cool. So this is going to load on up. This is a design calculator that I use for a project that I was working on. So the project that I was working on over here is a bed that lifts from the bottom to the top. So my goal was to specify a system that I could use to move a 60 kilogram bed to a height of 2 meters in less than 30 seconds. And that sounds really fast, but actually 30 seconds is pretty slow. So as we look at this, I've got my calculator over here, and I'll show you how I've laid this out so you guys can get an idea of how all of this stuff works. So true to form, like a consultant, all of my variables that I can change, I have in blue, and all of my static or calculated variables I have here in black. So I can go through and I can change the different diameters of the things that I'm using. So I'm careful to make sure that I use my units here so that I can keep track of everything. So I know my revolutions, millimeters, minutes, and that way when it comes time for me to look at my actual lift time, I can do all of that sort of stuff. I'm also looking at a variety of other things like the torque required to move things and whether or not the motor that I currently have specified will actually work. So the motor that I have specified in this particular system is a 775, just kind of a standard DC motor here. And this is how I went through and looked at it. So here's my 2 meter travel distance in centimeters. Here's my motor RPMs, which I'm pulling off of crud, I don't know where I am. Off of a motor data sheet. And so that tells me all of the things I need to know. So I'm looking at my 60 kilogram total frame weight here. And that shows me that I'm not able to do it. So I also, in the same one, I go down, I talk about all my electrical, and then I'm also looking at costs in the same thing. So this is showing all of the different things, my structural members, all of these things. So I recommend this is the way that I do it, but you can go ahead and build your own one of these. So this is just a normal spreadsheet. And most of the things in here that are calculated are just multiplication and addition and stuff, right? Here's a lot of multiplication and addition, but that's all there is to it. So that gives you an idea of how I go about solving this problem when I'm doing this in an actual engineering way. Okay, gear mounting. Here we are taking a look at McMaster data sheets, and they will show you the mounting distance for all of these things. So over here in the spur gears, you'll notice that it gives you a pitch diameter. This is an American part, so it's in inches. And then if I'm meshing that with one of the same, then I know that that's my mounting distance axis to axis. And if I'm doing a different sized gear, then I have that number and add it to half this number, and that gives my mounting distance between the two. That's how you do simple spur gears. If I'm doing bevel gears, you'll notice that it shows from the gear throat down here to the center of rotation here. And if I look on this gear as well, so they're showing two of the same gear, then it would be the same the other direction. But I may want to be using this to drive a different system. So if I have a different gear ratio with different numbers of teeth, then I would use those schematics respectively. Okay, cool. And you notice if I'm looking here, I am showing my tooth pitch here and my number of teeth. Tooth pitch, number of teeth, right? Those are absolutely necessary. And it should show module in there somewhere, but I don't see where it is. Cool. Let's talk about types of gears. I'm showing you one here on the screen, which I really love. This thing is called a harmonic drive. It's a zero backlash drive system. It's extremely high gear ratios in extremely low form factor. They're really neat, but it's kind of a specialty gear, so I'm not going to get too far into them, but there's tons of cool stuff on YouTube about how harmonic drives work. They are really, really neat. The other one here that I'm showing is what's called a Joyce-Dayton jack. And this is a combination of multiple gears working together, doing interesting stuff. So it's a worm drive driving this gear here, the spur gear, that drives a threaded rod for linear movement out of a rotational thing. In an extremely compact way, they're able to produce an incredible amount of force. It's super cool. And you see these sometimes in car jacks, but also they're powered frequently to move stuff like stages around, which is really, really neat because you can put a bunch of these all over the place and you can get that kind of balance. I am going to talk about the gears over here: spur gears, bevels, worms, differentials, planetaries, and well, my others are right here on screen. I want to talk a little bit about efficiencies because those are really important when you're thinking about your gear train. Spur gears are really high efficiency. Same thing with helical and double helical, which I'll talk about in spur gears. Bevel gears are also really high efficiency. Where your efficiency starts to drop is when you're starting to move things kind of in weird ways. And so your worm gears have very high ratios. So you can see the normal ratio range goes up to 75 to 1, which is crazy. But its efficiency could drop as low as 20%. So you're losing so much power out of there. Oh, it's a bummer. But yeah. So, but you could still maybe use it because it's very compact. It's a single set of gears, two gears meshing against each other. I'm not going to talk about cross helical, really, even though they're in this. I guess I am a little bit in the worm section. Spur gears are what you think of when you think of gears. They are like the most conventional gears. You can 3D print these, maybe not super well, but they can be done. They're simple, they're cheap, they're super easy to manufacture. They tend to be kind of bulky, particularly if you start chaining them together and getting these really long gear trains. They're a little bulky, and they always have parallel axes. But you can get really big gear ratios range off of them. So you can do 1-to-1, or you can do like, 10 to 100 and get that 10-to-1 ratio, which is crazy. Helical gears work a lot like spur gears, but as you can see, because I'm spiraling the tooth around the outside, they're a little more difficult to manufacture, but the tooth is longer even in the same form factor. And what that lets me do is have much higher torque and quieter movement because I'm engaging multiple teeth, more teeth at the same time. But they're more expensive to make. Cool. Bevel gears are what happens when you want to change the direction of rotation, and not that you're rotating against each other, but that you're changing the axes of rotation. So your shafts are always going to be coplanar. So like here, the plane is now like that, and they're pretty high efficiency. They're as high efficiency as a spur gear typically, and they're really common, and they're useful for things like drivetrains and that sort of stuff, as you have to make your movement go around a bend. And that bend is most commonly 90 degrees, but it doesn't necessarily have to be 90 degrees. You can get bevel gears custom made that do them at weird angles. Those are a pain in the butt to design, and I recommend against it if you can. You can get them in straight tooth gears like you see on the top here. And you can also get them in spiral tooth, which has a lot of the same advantages you get out of the helical gears from the previous one, and that you have the more tooth in contact at the time, so you can get more torque out of them and quieter movement, but they're just a bigger pain to make, and so they tend to be more expensive. Crown gears are a type of bevel gear, and that's where you have a spur gear over here hitting a 90-degree thing. So it's a subset of bevel gears, and the calculations are all the same. Conveniently, bevel gears and spur gears calculate exactly the same way. It's tooth to tooth ratio. Super duper easy on the calculations there. Worm gears are able to get these really, really, really high gear ratios because a worm gear is effectively like this one, which is a one-start worm gear, winds the same tooth around the shaft a bunch of times. That makes it a one-tooth gear. And what that means is that here where I've got, I don't know, what is that, 18 teeth, I would guess, on the outside there, where I've got that 18 tooth, I now have a ratio of 18 to 1, which if I need to do that with spur gears means like the smallest spur gear you can realistically have is about 8 teeth. Really 10 is better. So that means I need 182 gear over here, and this thing is going to be huge. It's going to be massive. So there's just not an efficient way to do it from a material space. You can't fit it all in there. Whereas this worm gear is super little efficient. It's tiny, and you can get pretty high efficiencies. But I would say a normal one-start worm gear like this is probably going to be in an efficiency range around 70%. So that's not great, but it's not terrible, and they're not super duper expensive to create. A similar thing here. This is kind of like these crossed helical gears are like a worm gear, but with many more teeth on them. So I can go from one tooth to a multi-start thread to a 4-start. Once I get above 4, it's not really a worm gear anymore, and it starts to become these crossed helical. But as you can see, it's just kind of a continuum from one to the next. Differential is one of my very, very favorite gear trains. And what it lets you do is it's typically a 5-gear system working together. And it diverts power from one input shaft between 2 output shafts. And this is really, really cool because it lets you drive around corners while one wheel on the inside needs to move slower. The one on the outside needs to move more quickly because you're kind of going around this curve. You need to be able to do that. And so I have a video for that that I will show. But before I move on to that, I want to talk a little bit about this thing that I've got in the bottom left there, which is what's called a south-facing chariot. And this was a device using differentials in the middle there. You can see that schematic. It was invented in ancient China. And it takes the output from the 2 wheels and measures them against each other. So instead of driving the wheels, a horse is driving the carriage, but I'm checking these wheels as they move with respect to each other to make sure that I have a gear system that always points south. So before you leave the stables, you set this thing to be south by shifting your wheels with respect to each other. And then no matter what turns and over the course you go, bumps and stuff, this thing always points south. It's just such an elegant gear system and proof of really, really brilliant engineering in ancient times. So neat, so neat. So let's take a quick look at a differential video. And I just want to show this so that you can kind of get an idea. This one does a little bit better job of showing that thing rotate. So you can see that I'm still getting a little rotation here on my right-hand side, but I'm getting a lot out of my left-hand side. Stop that there and head back to our thing. Planetary gears are another really cool one there. You've got that animated thing showing up there, and they're sometimes called epicyclic gears, but planetary gears is the common name. You have a sun gear in the middle, you have planet gears that travel around here, and you have what's called an annular ring around the outside, which is just a bunch of tooth on the inside of a thing. They're extremely compact, which is cool. And you can get kind of medium and high gear ratios out of them by changing the ratio of your sun gear size to your planet gear size. And you can do this with tooth ratio as well. The cool thing is, because they're compact, they can be chained easily coaxially. And this is how a lot of transmissions work, is that they chain these things coaxially and then they shift what's changing or what's the driven and drive gear out of there. So you can understand, if I keep this same drive gear, but I now fix my planet gears, my annular ring will start to rotate as well. And I can do this by breaking different things to get different rotations out of them. Okay, there's some other ways you can transmit power. Right here, I've got a rack and pinion. That allows me to take rotational energy and convert it into linear energy. And it's a very efficient way to do it, but I have kind of a limited range to do it. It's also important to know about clutches. Clutches are a method that allow you to engage and disengage rotational movement. So if I have a shaft that's rotating and I want to have a shaft that I can either rotate or not, a clutch is kind of that. It's basically a switch for power. And what it basically does is basically two plates, one rotating, and then when I put the other one in contact with it, friction overrides and it starts to rotate alongside. And this is neat if you want to be able to have something free rotate for a while and then engage to another thing where you're having an output of a thing. And you do this a lot of times if you have an internal combustion engine and you need your wheels to be able to stop. And that's because your internal combustion engine will stall if you stop it completely. So when you're driving a manual transmission, you disengage the clutch and it allows your motor to continue to free rotate, but your wheels can be stationary, and that's good because you don't want to continuously drive all the time because stoplights are important. Bearings are a really, really important part of rotational and linear movement because they allow you to constrain your motion in your degrees of freedom on some axes. So this is a plain bearing. You can see it right up here. I'm going to, hopefully it does it. And you can see I've got a picture of it there. And that allows rotation and translation along my shaft. And that's nice if I want to constrain things to move in a specific way. They're cheap, they're compact. They can't get to super high RPMs, and they do require lubricant. You can get what's called self-lubricating bearings, and that's because they put lubricant into the bearing already and it's slightly porous and it seeps back out. It's super useful. You can use them to hold a radial load, and what I mean by that is I've got my shaft and I've got my load going on the radius to that shaft, okay? Or an axial load, which means I have a load pushing along the axis of my shaft, and you can get both depending on the shape of the bearing. You can get slightly more expensive ball bearings. This is, you can see down there an unshielded ball bearing on the image, but you can see what I've got here is a shielded ball bearing. That just means they put a little piece of plastic in there to make sure dust doesn't get in there in case I'm operating it outdoors. Ball bearings are also really cheap. They're not quite as cheap as plain bearings, but they're still pretty cheap. They have much higher max RPM. So if you're going to be spinning something really, really fast, your ball bearings can go pretty dang quick. And they are typically rated for radial loads, not axial loads, but you can get ones that are rated for axial specifically or both. Needle and roller bearings are a little more expensive. I've got one here. You can see as I take it apart, I've got my rollers on the inside there. And it spins. This does both radial load and axial load. So I can load the crap out of it in this direction. I mean, I could probably put 100 kilos on this bearing and still have it free rotate really nicely. And I could probably do the same radially. So you can see that it kind of falls apart if I don't have it in a thing. I could probably put 100 kilos of load radially and it'll still rotate freely. So that's really cool that I can do it. It only does axial load in one direction, right? Like it literally falls apart the other direction. These are pretty expensive. So this bearing, I think, was about 15 euros. So they're awesome, but they're expensive. Air bearings are where you have a gap between two very precisely made materials and you pipe air into it. And then that air prevents things from touching. And you can get extremely high max RPMs, like hundreds of thousands of RPMs. But they tend to be really expensive because the manufacturing tolerances are so tight. You can also get these things called recirculating linear bearings. They look like this. They slide back and forth. And you can see a cutaway diagram of it there. That allows you to have that nice translational movement without getting rotation on any other axis. So if you have something that's moving along a system, these are a really nice way to do it. And they're not super expensive. I think this one was about 15 euros or dollars. Euros and dollars are about the same these days. Yeah, and so you can see over there on the right hand what the inside of a roller bearing looks like. Threaded rods are a really nice way to convert from rotational to translational motion. What you can see down at the top is this rod with just kind of a fixed thread on it. You can also get what's called ball screws, and ball screws use an internal channel where they move balls around, so it operates like a ball bearing, and they have almost no backlash. They're really, really, really cool for that. So in very high precision things, you often see ball screws used because they minimize that backlash. But they work the same way that a threaded rod does. And there's some math that, that operates that, and I wish I had time to go into it, but I'm already over time. Oops, we still have a long way to go because we haven't hit actuation yet. Oh, we're gonna pick up the pace here. I'm so sorry. Linear actuation, this is a steam engine. And it's showing you linear actuation that's then turning using linkages into rotational. I do want to talk about solenoids, pneumatics, hydraulics, and electrical actuators. I'm not going to talk about steam. Solenoids are just a magnet moving in a magnetic field. So you have an electrically controlled, an electric coil, and it moves a magnet. It usually is linear movement between 2 points. It can be spring return. That means while it's energized, it goes one direction, and it returns when you de-energize it. Or latching means you energize it, it goes one way, and you energize it with the opposite voltage, and it goes back the other direction. They have extremely high power draw when active and a huge inductive load. So you want to use a flyback diode. Google that. Otherwise, you're going to roast whatever power supply you have. I have learned this the hard way. Speakers are really, really similar to solenoids, but they allow you to have movement within a range based on the voltage and a spring that's going against it. Technically, you can do that with solenoids, but it's a little hard to do. And they're built to displace a fluid in waves to create sound. And a microphone works exactly the same way that a speaker does, but in opposite. So it uses sound waves coming in to look at an electrical signal coming out. And you have to amplify that in order to get a useful signal out of it. But that is, don't have time for that. Pneumatics and hydraulics are really, really cool and really useful. I use them for a lot of my stuff. I tend to stray away from hydraulics because you have to have high pressure pumps typically to do them. And so they tend to be pretty expensive. But they have extremely high force operation within a range. Pneumatics don't really do ranges very well. They operate really between 2 points, but they can be extremely fast, like scary fast, with relatively high force, which is really exciting. The forces correlate to the pressure that you put into them. And I would absolutely, for hobbyist purposes, use a speed controller. And that's a little needle valve that you put on the inlet, and that allows you to dial the speed down, which is important. If you open those all the way up, pneumatic cylinders move scary fast and you can hurt yourself. And you typically control them using solenoid valves that I talked about last week for easy electrical integration. Hydraulics tend to use very high pressures, so you need to have a very robust system that adds a bunch of weight. The nice thing about pneumatics is that they're very light. You can use electrical linear actuators. So there is such a thing as a linear stepper motor, which is basically this thing I have up here in the top, and it alternates electrical fields to move it across from north to south to north to south, north to south. And that gives you pretty precise motion. They're extremely easy to implement, but they're really expensive. So what I recommend doing instead is to use a rotational to linear system to drive your linear motion. You can buy those off the shelf, like this ball screw sliding table, which I pulled the image straight off AliExpress. Or you can do that, you can use a system. So this is a threaded nut that fits on a rod that's turned by a stepper, and that'll get linear motion provided you prevent it from rotating around, which you can do with one of these handy dandy linear rails. You can also get these things called down here, non-captive linear actuators, NCLAs. I have one right here. And what this is a stepper body that's hollow, but with a thread on the inside. So when the stepper rotates, it moves the threaded rod in and out. They're really beautiful, elegant machines. And I hadn't seen them until a couple of years ago, but they're really, really neat and they move things really well. We actually used those in our beds for the first generation and they did not work very well. They do a lot of force, but just not enough to move a bed. Cool, that's linear actuation. Let's do rotary actuation, even though we're already a little over time. So rotary actuation, I'm going to talk about this. You need to actuate stuff. It's often useful to have sensors. You can get those in rotary encoders, which I show here, and those have a digital output where you're looking at the signal coming in off of them to figure out where you are. And the number of counts dictates how much precision you get out of that. You can also just do it with in switches where you bump into something. And then you know you're there because you bumped all the way into it. Those are really cheap and really useful, and I have a drawer of them over there. You can also use Hall effect sensors. Those measure magnetic fields, and you could make your own rotary encoders by having a magnet pass by a Hall effect sensor and waiting for that Hall effect sensor to blip. Hall effects give a digital output, so you can just measure high or low on that signal, which is really nice. Cool. I'm going to talk about those actuators coming right up. That's now. DC motors. there you go, the 775 right here on the camera, and the 525, 555, whatever it is, 575 up there on the screen. This is a very conventional off-the-shelf motor. And the way that these work, brushed DC motors are extremely cheap. I mean, you can get them for less than $1, less than €1. They do require what's called an H bridge, which is this thing right here to operate. And an H bridge just to get control speed and direction. Otherwise, you could just power them and they just spin. It's magical. They're terrible for open loop control. And the reason for that is that each motor is slightly different. They rotate differently under load. So if you need to get any precision out of them, you need to have them with closed loop control. And that's really important. I've got a schematic over here of how they work. They use these brushes to alternate the polarity. So all you have to do is apply DC current to them and they start to rotate. Super cool stuff. You can also get what's called brushless DC motors, and these work slightly differently, where you're pulsing between different coils to get these things to move around. So you can see one deconstructed right here, all the different coils, and they require an electronic speed controller. They tend to have very high RPMs, and so they're often used in drone applications because you can control the speed of them really, really quickly, which helps with that stability and control that I was talking about before. They have a lot of the same problems with precise positioning that you would get out of a DC motor because they vary based on that thing. So I wouldn't use them for precision applications so much as I would use them for high speed applications. But they are really cool. You can also get DC motors that have been geared down for you. You can get these ones. These are originally, I think they were used for washing windshield wipers on cars. But they're extremely high torque. You can see there a worm drive hidden away underneath there. And they are just super duper high torque, which is great if you have something that you need to move at low RPM but high torque. And they tend to be pretty cheap and pretty compact. They're still not great for control, though the slower RPM makes position tracking a little bit easier. Servo motors are motors with integrated feedback, whether they're doing that with their own rotational encoders or whether they're doing it kind of the cheap way with a potentiometer. It depends. So microservos are the ones that I think are most accessible for most humans. And so they have their internal closed loop control in the form of a potentiometer that lives inside of here. And they have some gearing to give them much higher torque. But at the end of the day, it's really just a DC motor with a potentiometer that it drives. And it uses a pulse signal to guide where that goes. There's a lot of YouTube videos on how to do servo control, but they're really nice. They tend to have a limited range of motion. They don't usually go full 360 degrees, and getting them to run full rotations can be difficult. You can buy those, but those are less common and they tend to be a little bit more expensive to get full rotation servos. And even so, a lot of times they'll limit themselves to 5 rotations. So it's not a continuous rotation thing. You can get continuous rotation servos, but I would recommend doing stepper motors instead. Hey, a segue. So these use alternating coils to advance incrementally. So you alternate between coil 1 and coil 2 to advance 1 step. And the step, and so electrically, this is pretty easy to do. You use a stepper driver, which I'll talk about in the next slide. But you can advance your typical ones are 1.8 degrees. You can get high precision steppers that are 0.9 degrees. You sacrifice a little bit of torque for that higher precision. They tend to be pretty low RPM. They max out 1200 is a really fast moving stepper. I would never really want to push one past about 800 RPM. They tend to have pretty high torque given their body size, which is nice. And you can get very precise movement out of them, which means you can do open loop control on them with some reliability. They're not terrible for it. You can also use the coils to brake, where you apply a lot of juice to them and they hold everything in there, which you can't do with DC motors. But you do need to have a stepper driver in order to use them. So you have a couple of different options on stepper drivers. They kind of look like this. I've got some images up there. They're current limiting, but the torque in your stepper is voltage based. So you can put a lot of voltage into your stepper driver and then limit the current back down so your steppers don't overheat. And that's a really good way to do it. Also, most stepper drivers will allow you to do what's called micro-stepping, and that uses pulse width modulation to control how much is going into each coil. So instead of going directly from one coil to the next, which is the highest torque way of moving, you can kind of phase in and out, and that lets you get much higher precision. So if you're 32x micro-stepping on a 0.9 degree stepper, you can get that really, really fine movement around at 0.028 degrees per input. Now, you sacrifice torque by doing that. So there's always that trade-off. You're sacrificing torque to do that. But you can use them easily with open loop control, and you still need sensors for closed loop control. So you need a encoder for closed loop control, but we talked about that already. Cool. That's everything. I'm 10 minutes over. So dreadfully sorry. Let's end on a nice note. Engineering is all about persistence. Stuff is gonna break, but the rule of thumbs is if you can build it, you can fix it. So when someone knocks your thing off the table, don't get too sad. It's just an opportunity to rebuild it better this time. All right, I'm gonna start looking in chat for some Q&A. You thought I got rid of that picture, but I didn't. Sometimes I troll even myself. That was me when I could still get haircuts.